Okay, Calc kids, we are here again for 2.1 derivative of a function lesson notes part 2. And again, we are looking at these several things where we want to look at the graph of y is equal to f of x given, we want to find that given the graph of y is equal to f prime, and then we want to switch it around and then graph f prime of x given the graph of f of x. We're going to talk about one-sided derivatives and graphing the derivative from data. So let's scroll down to where we left off. Okay, so it looks like we are right here. So now I'm going to go over this pretty quickly, just save some time here. But if you notice, I have this graph of f of x is equal to x squared minus 3, and I want to sketch the graph of f prime of x. So if I want to sketch the graph of f prime of x, then I've got to get the tangent lines on the graph, and I want to say, all right, what is the slope of the tangent line? So if you look at, I put this tangent line on the graph, and it's in that neighborhood of that point -2, 1. So at the point -2, 1, you can see that I have a tangent line at this point, and the pink graph, I kind of went off of it a little bit. You can see that it's the tangent line at -2, 1, and the slope of that tangent line turns out to be -4. And as I go around here, I've got the tangent line here at where -1, and there's my green tangent line here. So the green tangent line has a slope of -2. And then I come around at x is equal to 0. Then I have that tangent line whose slope is 0. F prime is 0, 0. And then I go to 1, it's 2. And then again here, this last red one, that one is going to be then +4. So what we want to do is draw the tangent lines to get the slope of the graph of f of x. And then we're going to draw the graph of f prime. You can see this table is very helpful in that. So we come down here, and I've moved the table down from above, and you can kind of see that I have a lot of things on here, so try to excuse it. But I take the table and I graph this red graph here, and that red graph then is representative of the data that we found above from the slopes of the tangent lines from -2 to 2. So I plotted those points on the graph, and once I plotted those points from -2 to 2, I connected them with a curve. In that case, it is a line. And it turns out that the line's equation is y is equal to 2x. Okay, so it's a linear equation with the y-intercept of 0. So now, if you look at this, one of the things that's key about this is that when we evaluate derivatives, we're often looking at, well, here is where f prime is greater than 0 above the x-axis, and then here is where f prime is less than 0. And of course, right here is where we have f prime at m is equal to 0 here. At the origin on the graph of f prime is where it displays that f prime is equal to 0. Every time f prime crosses the x-axis is where you'll have f prime equal to 0. So in that case, only once. Okay, so paying a close attention to the signs. Now, if we look at this one, sketching the graph of the function f of x on the graph to the right, whose graph f prime of x is given below. So now, if you look at f prime of x, I was always typically looking at every graph and writing all over it, writing all the information that I could. But we have 3 characteristics that we want to include for our graph of f of x to the right, but it says f of 0 is 0. So we have that. So I went over here and I just put this point on the graph right here at the origin. Then the graph of f prime is given below, and f is continuous. So there are no breaks in the graph of f. So here's f prime. And we have 2 segments. One is over here and one is over here. And we notice that there is jump discontinuity in the middle. So now remembering that this is f prime, you have to say to yourself, all right, now the slope is equal to f prime is equal to y is equal to -1. It's a constant linear function, if you will. And then there's an open circle here, which means that at 1, open circles on both parts of this, there doesn't seem to be a point. That means that the derivative is not defined in this set. And you know that when we're talking about continuity of a graph, this is jump discontinuity. The limit does not exist, and the function value doesn't exist for this f prime graph. Now, so the other thing that I note is that when x is less than 0, when x is less than 0, your y is equal to 1. When x is greater than 1, I'm sorry, I said 0. When x is less than 1, then you have this case when m is negative 1. And when x is greater than 1, then m is 1. So it's kind of easy to be able to, okay, if we have to graph this, that's pretty simple. We know this point, f of 0, 0. We already have that graphed. And then if you look at it, I have it highlighted in pink for the graph to the left of 1, down at negative 1, y is equal to negative 1. Then that means the slope has to be negative 1 from this point. When x is less than 1. Actually, I have a point there, but I'll clarify that in a second. It says that f of x has to be continuous. So that as we are coming down on this left-hand side, you see where I have it highlighted pink? That's the same as the left-hand side over here in terms of slope is negative 1. So the slope of the left-hand side, all I have to do is graph the slope of negative 1 that goes through the origin 0, 0, f of 0, 0. And then once I get to 1, now keep in mind, this function is continuous. The slope isn't defined, but the graph is continuous. So I could have said right there, there's an open circle here, right? I'm just going to leave an open circle. Then I'm going to deal with the other side. So the other side, as I come down, this side has a slope of 1. So drawing that line, they meet at the same place. Now, being that the graph has to be continuous, I have to fill that point. There is a point of singularity that's missing. And you see that purple line that I have? To the left of 1, the slope is negative 1. To the right of 1, the slope is 1. And so that means if the slope were to continue all the way to x is equal to 1, I have that purple line, then that means it's got to end here at 1. And then the same thing is true with the slope is greater than 1. When x is greater than 1, the slope has to be 1. Okay, so there you have it. There it is. There you go. Now, keep in mind that the slope does not exist. When I look at a graph of the function, if I give you the function first, slope is now defined as a limit. A limit must be two-sided. So when we talk about slope being a limit, the limit as x approaches 1 from the left of the slope has to equal the limit as x approaches 1 from the right of the slope f prime. Well, on the left we have negative 1, on the right we have 1. So in this case, guess what? The slope does not exist then at 1. So it is a corner. When you have a corner like that, the slope doesn't exist. The one last thing that we have to talk about is we can consider a function y is equal to f of x, this differentiable on a closed interval a, b, if it has a derivative at every interior point of the interval, and if the limit is h approaches 0 from the right-handed limit, and if the limits exist, and the limit as h approaches 0 from the left-hand derivative at b exists. So you can kind of see what we're talking about. It depends on what interval we're talking about, but in this case, you can see we're going this way. b plus h is when h is less than 0. And then over here we have a plus h as you would approach this way. H is greater than 0. So remember what we're doing. We're trying to push b plus h to go towards h. As h goes to 0, you get to b on the right-hand side. On the left-hand side, as h goes to 0, you get to a. Okay, so here's one last problem I think we have two more to do. But the limit as h approaches 0 from the left of f of 0 plus h minus f of 0. Given this piecewise function, you have to identify which is the left and which is the right. Okay, so there you have it. So now the h, we're not talking about approaching x equals 0. We're talking about the fact that we're approaching, or h is approaching 0 from the left and from the right. Okay, so now with this one, from the left-hand side, we have this. And that's going to turn out to be, if you look and see what you have, it's going to be, let me write it down here. The limit as h approaches 0. Oh, wait a minute. I have a mistake here. I didn't mean to put a plus sign in there. This is going to be h squared over h, which is equal to the limit as h approaches 0 from the left of h, which is equal to 0. Okay, so now we have that answer. Now, for the right-hand side, let me scrunch this down a little bit. So you can see what I'm doing here is I'm saying, if you look at what I have here, h is less than 0 here, and I'm approaching 0 from this side, right? As h, I go from 0 in the middle to 0 plus h. H is being taken away, or h is negative, taken away from 0, or h is negative. So on the right-hand side, h is being added to, or h is positive. Okay? So you have to kind of understand what you're looking at here. Now, on the left-hand side, we have x squared. On the right-hand side, we have y is equal to x. So, on the right-hand side, we have the limit as h approaches 0 from the right of f of 0 plus h minus f of 0, same deal, over h. But now the function changes. We have y is equal to x. So we have the limit as h approaches 0 from the right of 0 plus h, replacing x, right? Y is equal to x, minus 0, replacing y is equal to x. So, and then this is over h. So this turns out to be the limit as h approaches 0 from the right of h over h, which is the limit as h approaches 0 from the right of 1, which is, of course, 1. Now, that means that the limit from the left and the limit from the right are not equal. Therefore, the limit for the slope cannot exist. So we would conclude that since the left limit is not equal to the right limit, so we would end up saying that so therefore the slope at x equals 0, or remember x is equal to a equals 0, does not exist. Remember, we have this f of a plus h minus f of a form for the limit. Does not exist. And that is simply because the left is not equal to the right limits. Okay, they must be the same. So the slope at 0 does not exist. I think I was clear enough about here, coming over this way to 0 plus h. Okay, all right, I'll leave that go. All right, last one. Using the alternative definition of the derivative, find the derivative of f of x is equal to square root of x plus 2. Now, what I'd like you to do is pause your video, try this, and then check back with me in just a minute after you're finished. Okay, so laying this out, we have f prime of a then is equal to the limit. We're using the alternative definition as x goes towards a of f of x minus f of a over x minus a. So when you do this, if you put in a right away, direct substitution, you're going to get 0 over 0. So what we're going to do is right away, we're going to multiply by the conjugate. So we have times the square root of x plus 2 plus square root of a plus 2 over square root of x plus 2 plus square root of a plus 2. Okay, now you can put parentheses around these, remembering that you must use them when you multiply, and these, of course. Okay, so now we have the limit. We'll simplify things as x approaches a. In the numerator, you're going to get x plus 2 minus a plus 2. Remember to put the parentheses around that second one especially. And then over, we have an x minus a factor. And then we also have this. We're going to tack this on x plus square root of x plus 2 plus the square root of a plus 2. Okay, now I'm going to simplify the numerator. In simplifying the numerator, let me make this a little smaller. We then have, this is equal to the limit as x approaches a. In the top, we're going to have x minus a. And that's going to be just x minus a, because it's going to be x plus 2 minus a minus 2. So in the top we have x minus a, and in the bottom we have x minus a times the square root of x plus 2 plus the square root of a plus 2. Okay, and I'm kind of going uphill here, but I'll fix it later. So, and then we'll cancel the common factors. Cancel the common factors, x minus a. And then we're on to the last step where we're taking the limit as x approaches a of 1 over the square root of x plus 2 plus the square root of a plus 2. So taking the limit of that, we're doing a direct substitution where x is being substituted with a. So that's equal to 1 over the square root of a plus 2. Sorry, I made a mistake here. This is going to be plus the square root of a plus 2. And bring this one over a little more towards the center. And so our final answer is, now here we're going to write this. F prime of a is equal to 1 over 2 square roots of a plus 2. Okay, I hope this video is helpful, and I will see you on the next appointed hour during the next appointed hour of class. And I hope you calculus students have a wonderful, wonderful night and a good day tomorrow. Take care. This is Alanator out.